Okay. So today also I want to kind of just make sure too, in the past, all right, when we graphed like quadratics and we graphed cubics, we did the best that we could to try and be as precise as we could, right? We really picked points that we knew were going to be on it, on our graphs and stuff like that, and we got a pretty good idea of the graph. For polynomials, what we're going to be doing today, it's going to be a little more, well, I should say a little less accurate, I guess I'll say, and I'll show you what I mean by that when we get to that point. But these are going to be just a little bit less accurate than what we've been doing with quadratics and cubics. And it's just because of the nature of the beast and stuff like that. In order to get the kind of precision that we would want to have, you would really need to know calculus. So if you ever do learn calculus, right, in your math career for whatever you happen to study, then you'll be able to kind of get more precise graphs with this. But for right now, and I'll show you where when we get to it, like what I'm talking about. But just understand, we're going to be a little bit less precise than we have been. Okay. So before we jump into the graphing part, I wanted to kind of do just a little like exploration of some of the functions that we know and some of the functions that we don't know yet. Okay, so specifically we're going to be looking at some functions. We're going to look at their domain, their range, and their end behavior. And we're going to use our graphing calculator. So if you have your graphing calculator handy, you might want to get that out. Okay. It will be helpful. We're going to start with a very simple polynomial, x. Okay. We also know x by what other name there? If it's just x to the, well, what's the degree of this polynomial? 1, right? And if we were to graph it, what would the shape be? A line, right? So this is something you've been very familiar with, probably since middle school, right? You guys start graphing lines, stuff like that, all right? But then we're going to move on a little bit, and we will talk about f of x equals x squared. We just spent a whole unit on that, right? We just finished that last unit. And we'll continue to talk about it a little bit here too. What is the degree of this polynomial? 2. And what would the shape of this graph be called? Parabola. That's right. Okay. So let's, and we'll do one more here. The one we just talked about yesterday, of course. F of x equals x to the third, right? All right. And this is degree 3, and it's a cubic, right? Cubic. Okay. So let's take a look at the graph of f of x equals x. Let's see, can I get the fit? Okay, that's pretty good. All right, what's the domain of f of x equals x? What is the domain of f of x equal to x there? Yeah, negative infinity to positive infinity. Okay, we'll give it an interval notation here. Right, the farthest left that we go, you can see we're just going to keep going left. And the farthest right that we go, you can just see we're going to keep going right there. So we're going to go to negative infinity to positive infinity. Okay. What about the range? What's our lowest y value that we're going to get to here, it looks like? Negative infinity. And then what's the highest y value we're going to get to? Positive infinity, yep. Okay. And then, end behavior, right? Let's talk about that. So remember, end behavior, it describes literally what it says. What happens at the ends of our functions. That means what happens as we go really far to the right, so as x approaches infinity. As we go far to the right, as x approaches infinity, what happens to our y values? What are they approaching? Infinity as well, right? They just keep going up. Okay, and as x approaches negative infinity, that means as we go really, really far to the left, okay, what happens to our y values? They are approaching what? Negative. Yep, negative infinity. Okay. All right, so far so good? That's your basic kind of properties of, a first degree or linear polynomial. All right, I'm going to change my graph up. Let's make it x squared. Okay. The parabola. Okay, so there's our parabola. Same questions. What's the domain of this? Negative infinity to positive infinity. Okay? What about this range? Is it the same as before? Negative infinity to infinity? Ah, right. So this one does not have a range negative infinity to infinity. Its range 0. It starts at 0, lowest value 0, up to positive infinity. That's right. So, and again, we'll include the 0 and then to infinity there. Okay? And let's talk about the end behavior then too. As x approaches infinity, that means as we go far to the right, what do our y values approach? Infinity. Positive infinity. Okay? And as x goes farther and farther to the left, as x approaches negative infinity, what does f of x approach? As we go further to the left, what do our y values approach? Yeah, positive infinity. That's going up. Still going up. You got it. Okay. So for x, our end behavior looked like this, right? Or x, our end behavior looked like this. As you went far to the left, you were going down to negative infinity. As you went far to the right, you were going up to positive infinity. For the quadratic, our end behavior looks like this, right? It's good, you know? As you go farther to the left, up to positive infinity. As you go to the right, up to positive infinity. All right. Let's look at cubic then. Okay, so I'll change it to x to the third, graph it. Okay. What's our domain here? Negative infinity to positive infinity. Okay. What's our range here? Is it 0 to infinity? No. Very good. Negative infinity to infinity. All real numbers. Okay. What's our end behavior here? As we go further to the right, as x approaches positive infinity, what does f of x approach? Yep, positive infinity. Okay. As x approaches negative infinity, as we go further to the left, what does f of x approach? Negative infinity. Okay, so that one's also kind of like the line, right? As you go further to the left, you're going to go down to negative infinity. As you go further to the right, you're going to go up to positive infinity. That was also like the line, right? The line was like this. Cubic's like this, right? And we have the quadratic like this. Okay, both go up. All right, what I would like you guys to do, those are the ones we're familiar with. All right, I'm going to have you do two more. Examine x to the fourth for me, please. And then also I'd like you to examine x to the fifth. Okay? So examine those two for me, please. You can use your graphing calculators. That's why I asked you to get them out. Okay, to help you with that. Okay. Give me the domain, give me the range, and please give me the end behavior too. And I'll come around and help if you get stuck on something. Sorry, Isaiah. Oh, yes, you need like the top. Yes, here, sorry. So see what you come up with there. What's the end behavior? You might be able to just figure it out. Yeah. Okay, so syntax. Syntax Basketball can wait.
Yeah, Blake.
I know it's probably more interesting than what we're doing right now, but I want to make sure you're okay with this stuff too. Okay. Right hand. Yes, gentlemen. These things can wait. Let's go. Sorry, I didn't mean to call you out. No, I should have said something. All right so far?
Hey.
You can? I know it's got like 4 letters there, but that's because there's like 4 different modes, and it'll give you any one of those 4 depending on the mode that you're in. So. Okay, you like 1 more minute. Is that okay to cook these?
Yeah.
Yeah.
Look at this man.
It's my dad.
Wow.
We have different last names, so.
Imagine being Mr. Burger.
Mr. Berger. He probably makes a lot of money. Those authors writing textbooks. I mean, look at all these textbooks they just sold. This
Yeah.
lasts a little.
Yeah, that's true.
They get paid to torture teenagers.
Yeah.
That's living the dream right there, I'd say. Actually, I guess I get to do it too.
I'm gonna start making textbooks.
They can torture them through me.
I'm gonna just like research everything that everybody does history.
They get to remove themselves from the torture. I have to watch it.
Everything that is
Are you good with that, Isaiah? Are you, you're still looking at this? We'll just post this up then. All right, so let's see how we did. All right, should have gotten something like this. I'll zoom in on it there. Okay, so domain for both negative infinity to infinity. Range 0 to infinity for x to the 4th, negative infinity to infinity for x to the 5th. Okay, end behavior. For x to the 4th, both ends go to positive infinity. For x to the 5th, right end goes to positive infinity, left end goes to negative infinity. Okay, so there they are in toto. Okay, so, is that a question? Yeah. Do you notice any relationship among these different polynomials? How might we be able to categorize or classify or organize these, right? So, what do you say? Right, Arshia? Okay, so the odd numbers, we can kind of like break them into one category, okay, because they all have the same domains, they all have the same ranges, and their end behaviors are also all the same. Okay? Is the same thing true for the evens? Do the even powers all agree too? Are the domains the same for the evens? Yes. Are the ranges the same? Yes. Are the end behaviors the same?
No.
The answer is yes, they are. Okay, they are. They are. Okay, just because Mr. Whitmire asked the question like he's looking for a no, sometimes he does that to mess you up. Okay? So make sure you know the answer. Don't just fall on its way out. Anyway. So this is a technique we're going to be using because let's say, for example, that I wanted you to graph like x to the 7th, right? Well, you can immediately know in your head, okay, if I want you to graph x to the 7th, I know x to the 7th is going to kind of look like x to the 5th or kind of look like x to the 3rd. It'll have the same domain, the same range, and the end behavior will be the same. Okay? All right, so all the odd functions kind of have like the little, I'm a little teapot kind of thing going on with their end behavior, right? All right? As you go really far to the left, it goes down. As you go really far to the right, it goes up. All right? And then all the even functions, x to the 2nd, x to the 4th, x to the 6th, x to the 8th, x to the 10th, those all are like, kicking a field goal. It's good kind of thing, okay? They both go up from left to right. Okay? So, let me put this in a summary. All right, we'll make a little table here. Okay, now, if your lead coefficient, of course, all of our lead coefficients here were what? What were all of our lead coefficients for these problems? What were all the lead coefficients for these polynomials here? 1, right? 1. So if the lead coefficient is positive, of course, these will be the same. These will be in agreement. But if our lead coefficient is negative, if we get a negative in front, what does that do to the function? What kind of transformation do we experience when we put a negative in front of our lead term? What does a negative in front of our lead term do? Reflects it over the x-axis, right? And so we're going to have our end behaviors flip-flop then when that happens, right? So if it did go to positive infinity, it'll go to negative infinity. If it did go to negative infinity, it's going to go to positive infinity. If both went to positive infinity, both will go to negative infinity, okay? And then, of course, the degree also affects this too. And I'm going to put this like right down the center like that. Ugh. Okay, so the degree, that's the highest power. Okay, so we'll say if it's odd versus if it's even, as Arshia correctly kind of categorized things there. Even and odd. Okay, that's what we're looking at here. Okay. So if we are odd and positive, we're going to get something that looks like this. Okay. And so then as x approaches infinity, f of x will approach infinity. As, oh, I really did not write this big enough. As x approaches infinity, f of x will approach infinity. As x approaches negative infinity, f of x will approach negative infinity. Okay? So it's like the I'm a little teapot kind of thing, right? All right, then for negative, right, this will flip. And it'll look something like this. Okay? And so then as x approaches infinity, f of x will approach negative infinity now. And as x approaches negative infinity, f of x will approach infinity. Sorry for squeezing that in so much. All right, and then for evens, right, that's where, like, the field goal, right, it's good. Okay, even and positive. As x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches infinity still. Okay, so both sides go up. It's good. Okay, even and positive. Okay, and then for the even and negative, you're going to get end behavior like that. So as x goes to infinity, f of x will go to negative infinity. And as x goes to negative infinity, f of x will go to negative infinity. Okay, just like that. Okay. And with that introduction, we can now talk about, finally, sketching the graphs of a polynomial. Okay. With that kind of introduction, we can now talk about sketching the graph of a polynomial. Any questions on this so far? All right, so we have odd positive, odd negative, even positive, even negative. It's like a little dance. Okay? Just you don't move your feet. So it's about how well I dance. I'm a math teacher. All right. So let's move on to an actual problem then. We're going to sketch the graph of f of x equals x times x plus 2 times x minus 3. There's going to be three major pieces of information, three major steps we want to take when we go to sketch this graph. Okay, step one, and it's not really in a particular order, although you'd want to do, well, you don't have to do this one first, but it's not a bad idea. We'll just do it since we just talked about it. Okay, let's talk about the end behavior. Okay, now, what did we just establish we need to know in order to find the end behavior? You need to know the... Okay, the a value, right? We need to know a, the lead coefficient, and we need to know the degree, okay? So looking at this, all right, looking at this, what's a going to be? 1. How do you know? There's nothing in front of any of the x's, right? It's a 1x, it's a 1x, it's a 1x. So 1 times 1 times 1, it's going to be 1. Yeah, so a here is 1. Very good. Okay? Which means it's greater than 0. It's positive, right? Okay. What about the degree? What's the degree of this polynomial going to be? 3? How'd you get that? I see x to the 1, x to the 1, x to the 1.
Well, like, if we multiply the x's together.
X times x times x, x to the third. Exactly right. The degree here is 3, which is odd. Okay. Very good. Exactly right. That's exactly the kind of mental math that you can use in order to figure out the degree here. Okay? This polynomial is not in standard form. But you don't need to go through the pains of like pulling this out and then multiplying the x and dividing that term. You don't have to do that. All we need to know is what the lead coefficient is. Take the lead number for all the x terms and just multiply them together. 1, 1, 1. Multiply together, you get 1. Same thing with the x. Just multiply the x together. There's an x here, there's an x here, there's an x here. So x times x times x, x to the third. Okay? That's the highest power we're going to get. So, since we have positive lead coefficient, odd degree, it's going to look like this with our end behavior. So as we go to the right, we're going to go to infinity. As we go to the left, we're going to go to negative infinity. So I'm just going to write that out here. As x goes to infinity, f of x will go to infinity. As x goes to negative infinity, f of x will go to negative infinity. Okay, perfect. So that's good to know. That's our end behavior. Then the next step we're going to do here. So actually, questions on the end behavior before I move on. Questions on how we found the end behavior there? So it's like the I'm a little teacup. Okay. All right. So then zeros. Okay. How do we find the zeros of a function? If we're not given the graph, how can we find the zeros of a function? What can we do? Set. Yeah.
Those things equal to 0.
Yes, yes. Okay. What is a 0? It's where the graph crosses the what? X-axis. What are the y values on the x-axis? What are the y values on the x-axis? It's 0, right? If you're on the x-axis, your y values are 0. So we set f of x. We put 0. We replace f of x with 0. So we say 0 equals, bless you, x times x plus 2 times x minus 3. Okay? And then Teresa is exactly right. She was already one step ahead there. Since we have 3 things multiplying together that equal 0, we could say, then x must be 0, or x plus 2 equals 0, or x minus 3 equals 0. Okay? Now, there's one of our zeros. That's done. And then you can just solve these. Subtract 2, add 3. So you get x equals negative 2, and x equals 3. Okay? These zeros give us some actual points to plot. And so I'm going to go ahead now and plot those points over here. Okay. So 0, negative 2, 3. Okay, there are my zeros. I can also go ahead now and graph my end behavior. All right? How are we going to graph that? Well, let me just show you here. So our end behavior says as x approaches infinity. So as I go really far to the right on my graph, well, here's the farthest right point that I've got. I'm going to go to positive infinity. So from here, which direction should my graph go? Up. Okay, something like that. And then for the other part, as I go really far to the left, so here's my leftmost 0. I should go which direction?
Down.
Towards negative infinity, right? Down. Put some arrows. What's the only part of the graph that we're still missing?
The middle part.
Yes, the middle part. What's going on between the zeros? We've got the ends. We've got the zeros. We just got to figure out what's happening here. Do we go up? Do we go down? Do we go up? Do we go down? Okay? We need to know that. And that's why we need this third part. And I just call it the middle behavior. What happens in the middle? Okay? How can I figure out what's happening between these zeros here? What could I do? Okay, plug in a point. What would be a good point to pick here in this interval? So yeah, negative 1, right, because we're on the left part of the x-axis. So negative 1, okay? I don't know what the y-coordinate is, though, so I'm just going to pick the x-coordinate negative 1. So I'm going to plug in negative 1. So we'll do f of negative 1, which is going to be negative 1 times negative 1 plus 2, bless you, times negative 1 minus 3. So I'm just plugging in negative 1. I'm picking this point right here to try. Okay, it's between the two zeros there. I'm just going to see what y value we get. And that'll give us a point. Okay, at this point, if you want to use your calculator, you can. Let's see here. It's going to be negative 4 times 1 times negative 1. So positive 4, I think. Make sure I did that right. Yes. So we've got a point, negative 1, 4. So negative 1. I guess I'll just count by ones here. Well, let me hold off. I'm going to get my other 0 too, or my other middle behavior. All right, we better check this interval too, right? So what's a good number to pick in this interval here?
1, 0.
Okay, we can do 1. Yep, let's pick another. So we'll do f of 1 now. Oh, I see. Were you talking about this one first, Teresa?
Yeah, I was like,
Okay, I'm sorry. You weren't doing this. I see.
Yeah.
Okay, yep. Okay, I got you now. Never mind. Okay, yes, you were right. We were going to need to use 1 or 2 here, or 1.5 if you like, but yeah, any number in this interval. So f of 1, let's see here. So that's going to give us blah, 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 negative 2 times 3, negative 6 times 1, so it's negative 6. So 1, negative 6. Okay, so we can probably get away, since I need a y value of 4 and a y value of negative 6, I can probably get away by counting by ones here. So I'm just going to do that on my y-axis. So 1, 2, 3, 4. And then negative 6 at 1, so 1, 2, 3, 4, 5, 6. Okay, and now that we have those, you can just kind of connect the dots. So we know we have to come up to this point, but then go back down through 0, 0. And I got to go continue down through this point, but then I got to go back up Okay, that point right there. Okay, and there is a sketch of our polynomial. Okay, there it is. Just connect the dots from left to right. Okay. Any questions on that? Okay. Is anyone still writing this information down? I'm going to block it up. No? Okay. So, there it is. Right there. Graph it. Does that look pretty good? Looks all right, right? There's our end behavior. We have a hump there, right? Peak, and then a valley, and then goes off to infinity. Now, here's what I was talking about earlier. Second trace, maximum. I'm going to find the actual point for this peak. Go to the left, hit enter. Go to the right, hit enter. Guess, hit enter. Okay. Look at the maximum coordinate. Look at the actual coordinate for the top of this peak. Okay. Is that the same as what we have here for the top of our peak? Our top is at -1, +4. Is that the same? No. Is this a rounding error on the calculator's part? No. Okay. This is not the highest point in this little neighborhood right here. This is not the peak here. This is the coordinate for the peak. Okay. Let me show you the valley there. So we'll do the minimum command. I'll go to the left, hit enter. Go to the right, hit enter. Go down to the guess, hit enter. Okay. There's the coordinate for like the little valley. 1.7863012, -8.208821. Is that the same coordinate as what we have right here? No. Okay. Is this a rounding error on the calculator's part and we're right? No. The calculator is right. This is the lowest point right here. Okay? What we're doing here is a sketch. All right? And that's the best we can do with what we're going to be learning in this class. All right? We've kind of reached a limit here. Okay? Later, if you decide to move on and you take calculus, you will be able to find the precise coordinates of this point using calculus. Okay? It has to do with the slope of the function and stuff like that. Okay? But we're not going to worry about it for right now. Okay? So you don't have to worry about that. But if you do plan on taking calculus, you will learn how to find those points. They're called relative extrema. That's a relative minimum. That's a relative maximum. You can understand why we call it a relative minimum, right? Because it's like a low point, and this is a relative maximum because it's a high point. But it's relative because is this the highest point of our graph? Is this going to be the highest point of our graph? No, because our end behavior keeps going to infinity, right? But relatively speaking, in this neighborhood of points, that is a maximum, right? Same thing here. This is not the lowest point of our graph. We're going to keep going down, but relatively speaking, this little neighborhood of points, that is a minimum, okay? If this was the highest point, we would call it the absolute maximum. And if this was the lowest point, we call it the absolute minimum. But they're relative maximums or relative minimums for now. Okay. That's more than you need to worry about for right now for that. Questions on the graph sketching here? If that was enough for you and you feel good to go, I'll go ahead and give you guys the homework assignment. If some of you are still feeling like, Mr. Wood, I'd like to see one more, I'll do another one for you guys. Okay? So I'm going to put the homework assignment up. Your choice, whether you decide to start working on it now or if you want to follow along for another one, your choice. Okay? So we put up the homework assignment and you guys can make that call. I have spare books in the back there if you want to work on it. It'll be in the book. Okay? Yeah, questions?
So like it's acceptable to do it the calculator way as long as you like find the end behavior?
Yes. I would recommend you use the table though to get some points and not like the actual max and min because it's going to be like sometimes nasty numbers. So.
Yeah, of course.
But yes, you absolutely can use a calculator if you'd like. Yep.
That just makes it a lot easier.
Yeah, no, I understand. And you know, there's that for sure. But I wouldn't feel like I did my job if I didn't show you the non-calculator way to do it, you know?
Yeah, that makes sense.
All right.
It's not that I don't understand it, it's just that it's like way easier with the
Understood. Oh, I didn't put it in yet. That's right. All right, so it's going to be out of section 5-2 in your book. Okay, which I have to look at the page number now because I don't have it. numbers, ooh, let me make sure. 9, 10, and 14. Sorry, numbers 9, 10, and 14 on page 189. Okay, so if you're feeling good, go ahead and get started on the assignment. Okay, it's just those 3 problems, but 2 of them are graphs. And then this one, you're given the graph and you're asked to come up with the equation. Okay, so
Can I use the bathroom?
yeah.
Can I go back?
You can go since you're going to different places. That's fine. I'm assuming. Okay. All right. Did anyone want to see another example?
What, do we need graph paper for the number?
Potentially, yes. You can just flip your notes over if you want to and just do it on the back of that. Did anyone want to see another example? I can show another example if anyone was curious about another example. We're all feeling okay? Yes? Okay. I'm going to do one anyway because I said I would, and since I'm recording it, I'm going to show it to those people. So you guys can just kind of tune me out. I'm sure you're very good at that at this point. So I'm going to do one more here. So if you want to follow along, please feel free. If not, then forgive my talking here. All right, so I'm going to do one more here, and I'll do f of x equals negative x squared times the quantity x minus 4. Okay? So another polynomial here. Again, we'll identify the end behavior first. Okay? And so again, when it comes to the end behavior, we need to know 2 numbers, right? Those 2 numbers are the degree and the lead coefficient. All right, so let's figure out, let's see, what did I do first here? I did the lead coefficient here first. Let's do that. Okay, so in this case, I can see here I've got a negative 1 in front of my x squared, and then I have a positive 1 in front of the x. So negative 1 times positive 1 is going to be negative 1. So a is equal to negative 1, which is going to be less than 0. Okay, so we're negative lead coefficient. Okay, then the degree, well, again, we have to use our imaginations here, right? X squared times x, that's going to be x to the 3rd. So the degree is 3. Or in other words, that is odd. Okay, so negative lead coefficient, odd degree. When we go to our little table here, right? Negative lead coefficient, odd degree, that's I'm a little teapot. One goes one direction, one goes down. One goes up, one goes down. Okay, so that's what we're going to do here. As x approaches, this is going to be, well, I'll just draw it here. Looks like that, what our end behavior will look like. So as x approaches infinity, f of x will approach negative infinity.
Mr. Woodcock,
Question?
when we mix back, can I go to the bathroom?
Yes. As x approaches negative infinity, f of x will approach positive infinity. Okay. So as you go far to the right, we go down. As you go far to the left, we go up. Okay. So there's end behavior. Next step, we'll find the zeros. Okay, remember again, we call them zeros because it's when y equals 0. It's where the graph crosses the x-axis. Y equals 0 there. So we'll just set this function equal to 0. Okay, and then we'll set each one of those factors equal to 0, right? We have 2 things that are multiplying to give us 0. So we'll set negative x squared equal to 0. We'll set x minus 4 equal to 0. Okay, and we just solve. Here with the negative x squared, well, it's really a negative 1 in front, so I'll divide both sides by negative 1. So those cancel. I have x squared equals 0. And I'll square root both sides. So x equals, well, normally in an equation, if you're square rooting both sides, you put a plus or minus. But with 0, 0 is not positive or negative. It's just going to be 0. Okay? Then we'll add 4 to both sides. And so x equals 4 is your other 0. All the problems that you're going to have today are going to be factored already. So you don't have to worry about like not being in this form where it's already factored. They'll all be factored. So we'll take our zeros here. we'll plot these zeros. So a 0 at 0, and a 0 at 4. So 1, 2, 3, 4, right there. Okay. Got our zeros plotted. And now for our end behavior, right, as I go really far to the right, so my furthest right point is right here, I need to go towards negative infinity, so I got to go down. Okay? As I go really far to the left, there's my leftmost point. I need to go up. Okay? And now I need to determine the middle behavior. What's going on between these two zeros? Do I go above? Do I go below? Which one is it? So we'll pick a number in this interval here. Let's see, I've got a choice of 1, 2, or 3. I'm going to pick number, well, and really any fraction thereof, but I'm going to pick 2 because it's like right in the middle there. So for the middle behavior, okay, I'll pick x equals 2. Okay, so I'll do f of 2 equals, let's see, negative parentheses 2 squared, 2 minus 4. So again, that 2 replaces the x. There's still going to be the negative in front there. Okay, and we'll just do this here. 2 squared is 4, negative 4 times 2 minus 4 is negative 2, so I get 8. Okay, since I have a y value of 8 here, I'm probably not going to count by 1s on my y-axis. 8's kind of a big number, so I'm going to count by 2s. Okay, so we have the point 2, 8. So 2, 8 will go right there. And I just connect the dots, right? I got to go from left to right, I got to go kind of, I'm just going to touch that 0, and it goes right back up, then hit the 8, and then it goes back down, hit the 0 right there. Okay? So this is an example right here of like a double root. Okay, 0 kind of happens twice, and that's why it kind of just comes down and kisses and goes right back up. Whereas here for the 4, it goes through the 0. Okay? And so there's your sketch. If you want to extend your arrows, you can. You know, go further up, further down this way if you want to. But that's a sketch of it. And if we put it in our graphing calculator, you can take a look and see that it does kind of match up there. All right. Very good. Get the video stopped here. Question, Isaiah? Yep, I'll be right there. Sorry, thank you for waiting too. I'll be right there.